Hi everyone, welcome back to Math 251. Today's mathematician of the day is Himahurako Iwao, who was a Japanese mathematician and computer scientist who used her math and computer science skills to calculate the world's most accurate representation of pi, 31.4 trillion digits. Wow, that is a lot of digits. And our math history fact of the day is that there is also a cubic formula, kind of like the quadratic formula, that was published in 1545 by an Italian mathematician named Cardano. This cubic formula is quite long. It is much longer than the quadratic formula. And there's actually a quartic formula, that is the fourth, but it's been proven that there is no such thing as a quintic formula. So there's no such way to compute the fifth roots of polynomials with a single formula. So today we are discussing something called related rates, and related rates are usually word problems when two variables are changing at the same time, and we want to find out one of these variables basically. So we're going to do an example, and then we're going to go through a procedure for how to solve these problems. So an oil rig springs a leak in an ocean, thanks BP, and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area around the patch increasing when the patch has a radius of 100 meters? So here we have two variables that are changing, radius and area. And we want to know how fast the area is changing when the radius is 100 meters. So let's write down what we know. Well, I'm going to define my variables. I'm going to say that r of t is the radius at a certain time, and I'm going to call a of t the area. So what do we know? Well, it says the radius increases at a rate of 30 meters per hour. So this word increase is important because it tells us that the derivative of the radius is 30 meters per hour, right? If something is increasing at a certain rate, we know that that is its derivative. So we know that r prime of t is equal to 30. And we want to know it says we want to know how fast the area around the patch is increasing. So this is a prime when r is equal to 100 meters. Okay, well, what else do we know here? How are these two variables related to each other? Well, the area of a circle, since we are dealing with a circle, is pi times r of t squared. So the area of this circle around the rig will always be pi times the radius squared. So this is the relationship that we are going to be working with. But in this relationship, right now, I just have a and r, but I want and I know a prime and r prime. So to get a prime and r prime, I'm going to differentiate both sides. In order to get what I want. So I will have on the left side, I will have a prime of t is equal to pi times the derivative with respect to t of r of t squared. But r of t is a function. It's not a single variable. So on this side right here, I'm going to have to use the chain rule. The reason that I didn't have to use the chain rule for a is because I just had a itself and not a inside of another function. So if I use the chain rule here, this gives me my outer function is equal to x squared, and my inner function is equal to r of t. This makes f prime equal to 2x and g prime equal to r prime of t. So if I have f prime of g times g prime, this gives me 2 r of t times r prime of t. So plugging this back in gives me a prime of t is equal to pi times 2 r of t r prime of t. So this is what I have now, and from here I want to know a prime when r is equal to 100. So I first need to plug in the variables that I already know. So I know that r prime of t is equal to 30. I can go ahead and plug that in right here. And I also know the radius. I know that I'm trying to find the area when the radius is equal to 100, so I also know what the radius is. So I get a prime of t is equal to pi times the radius, well, actually 2. So I have 2 times the radius, which is 100, times 30, which is r prime. So this is 6,000 pi, and our units here are meters squared per hour. So the area of this circular patch is increasing at a rate of 6,000 pi meters squared per hour when the radius is 100 meters. All right, so if you're a little bit overwhelmed with this problem, if you're not, we are going to write down a procedure that will work every time with related rates problems. So our first step that I actually forgot to do is to draw a picture. Pictures always help. And write down what I know and what I want to know. This will help us to organize information. The second step is we write the equations that expresses the relationship between the variables. In this case and above, we had the area is equal to pi r squared. So write down the equations. It's possible that there's more than one that expresses the relationships between the variables. Oops. Between the variables. Next, we introduce what we call related rates by differentiating the appropriate equation with respect to time. All of these problems, our independent variable will be time. By differentiating the appropriate equation with respect to time. Next, I substitute known values in and solve for the desired quantity. Finally, I check units and make sure the answer is reasonable. For example, if we had gotten a negative number in the example we just did, we would have known that something was wrong, since I know that my area was supposed to be increasing. So if I go back to this first problem and label these parts of the procedure, I forgot to draw a picture, but I did write down what I know and what I want to know. That was here. Then I wrote down the equation that expresses the relationship. That was right here. I differentiated both sides. That was right here. And then I substituted my known values to solve for the desired quantity. And my units were reasonable, right? The area has a unit of meters squared, and our time is hours. So that's why our units were meters squared per hours. And it's reasonable, right? It's pretty big, but our radius is big at that point, so looks good to me. Okay, let's do another example. Two birds approach a nest, one flying due west at 120 feet per minute, and the other flying due north at 150 feet per minute. Assuming they are both flying at the same height, how fast is the distance between the birds changing when the westbound bird is 180 feet from the nest, that's typo, and the northbound bird is 225 feet from the nest? I don't know why I misspelled nest twice, but that's okay. All right, so first step is let's draw a picture of what is going on. So I'm going to draw a triangle since that is what we have here. So if I call this right here my nest, it's beautiful, I know. And I have a bird that is flying due west. So I have a bird right here. Chirp, chirp. And I'm going to call this bird A. And let's label the distance between bird A flying west and the nest x of t. Then I have bird B down here who's flying due north. And let's call the distance between bird B and the nest y of t. Okay, and then we'll call the distance between birds A and B z of t. I know what you're thinking. Wow, Amanda, such beautiful birds, such beautiful nest. Why aren't you an artist? Yeah, I know. It's ridiculous, right? Okay, and then we also have another triangle that we are dealing with, right? So the triangle that we want is when the westbound bird is 180 feet from the nest, and the northbound bird is 225. Okay, so if I have this triangle when the distance between bird A and the nest is 180, and the northbound bird is 225 feet from the nest, then how can I solve for this distance z? Well, I use the good old Pythagorean theorem. So if I plug in 180 and 225 into the Pythagorean theorem, I get z is equal to 288. We'll see why this is important. Okay, so that is the first part of step one. Now I'm going to write down what I know and what I want to know. So we have a lot of information here. So I see that the bird A is flying due west at 120 feet per minute. So that means that the distance between bird A and the nest is changing at a rate of 120 feet per minute. So we know that is x, so dx dt is 120. We also know that we have the bird flying north at 150 feet per minute. So that will be dy dt is equal to 150. We also know that we want to find, we want to find the quantity, which we'll get to in a minute, when our x value is 180, since I want to be 180 feet from the nest. And the northbound bird is 225 feet from the nest. So this is what I know. And what do I want to know? Well, I want to know how fast the distance between the birds is changing. So the distance between the birds here is z of t. So I want to know z prime of t. Or z dz dt. That is what I want to know. All right, that was the first step, drawing a picture and write down what I want to know and what I know. Next, I need to write down the equations that expresses the relationship between the variables. So how are x, y, and z related to each other? Well, x, y, and z are in a right triangle. So x, y, and z are related through the Pythagorean theorem. So I know that x of t squared plus y of t squared is equal to z of t squared. This is the Pythagorean theorem. And that is how all of these variables are related to each other. Next, I need to take the derivative with respect to t of everything. So I take d dt of x of t squared, the derivative with respect to t of y of t squared, and the derivative with respect to t of z of t squared. Now on each one of these, we are going to have to use the chain rule since x, y, and z are all functions. They are all changing. They are not single variables, so we have to use the chain rule on all of this. All of these are the same, right? We have x squared, y squared, and z squared. So I'm just going to show the chain rule for x, and it will be the same for y and z. So when I take the derivative using the chain rule of x of t squared, that means that my outer function will be x squared. My inner function will be x of t. That makes g equal to 2x and g prime equal to x prime of t. So f prime of g times g prime is equal to 2x of t times x prime of t. And like I said, the derivatives of y of t squared and z of t squared are the same as this, just replaced with y and z. So when I take the derivatives, I get 2x of t times x prime of t plus 2y of t times y prime of t is equal to 2z of t times z prime of t. That is me taking the derivative of everything. So then let's go ahead and plug in what I know. So I want to know, again, I'm trying to solve for z prime of t, or dz dt. That is what I'm going for. But I have a lot of information here, so let's go ahead and plug that in. I know that x of t is 180. So I get 2 times 180. X prime of t is 120. And actually, we have to be careful here. Is x of t positive 120 or is it negative 120? Well, the distance between the bird and the nest is decreasing. So actually, this dx dt is negative because the distance is decreasing. So negative 120 plus 2, our y value is 225. And our y prime, since the distance between bird B and the nest is decreasing, this is also negative 150. Is equal to 2z of t, we found here in this triangle right here, to be 288. And then z prime of t is what we're trying to solve for. So if I divide both sides by 2 times 288, I get that z prime of t is equal to, if I do the math, negative 192. And what is my unit here? This is how fast the distance between bird A and bird B is changing. So we are in feet per minute. Negative 192 feet per minute. Does this make sense? Well, the negative 192 makes sense because our distance is decreasing. And if I have, 120, 150, 192 makes sense. And our units look good. Okay, let's do another example. As you'll see today, these related rates problems come in all sorts of different varieties with different shapes, different situations. So these 4 examples that we're doing today are all pretty different from each other. All right, so in example 3, coffee is draining out of a conical filter at a rate of 2.25 cubic inches per minute. If the cone is 5 inches tall and has a radius of 2 inches, how fast is the coffee level dropping when the coffee is 3 inches deep? Okay, so let's draw a picture. We have a cone here, like this. And we know that the cone is 5 inches tall, and it has a radius of 2 inches. That is our cone. If I were to take a cross section of the cone, meaning if I were to slice in and take like this triangle right here, let's draw a picture of what that triangle would look like. So if I were to draw this, I know that the radius is 2 inches and the height is 5 inches. But my coffee is draining out of this filter. So if I were to take a cross section of the coffee draining out of the filter, it won't always have a radius of 2 inches and a height of 5. So if, say, the coffee is at this level right here, that is changing since our coffee is draining out, then I'm going to call the radius here R, and I'm going to call this height here H. All right, so that was our picture. What do we know? Well, we know that the coffee is draining at a rate of 2.25 cubic inches per minute. So our volume is changing at a rate of negative 2.25 cubic inches per minute. So we know that dV, if V is volume, dt is negative 2.25 cubic inches per minute, since that is the rate that it's decreasing. And we also know that we want to find something when the coffee is 3 inches deep. So we want to know, so the height is 3 inches. And we want to know how fast the coffee level is dropping. So that is H over here on this triangle. So I want to know dH dt. dH dt. All right, how are all of my variables related to each other? Well, I have a cone here. So the volume of a cone, which is what I'm dealing with here, is equal to 1/3 pi r squared h. 1/3 pi r squared h. For any of these formulas, by the way, I do suggest putting them, if you're allowed a note card on the final, putting them on the note card, or they will be given to you. So don't worry about memorizing the all of the different formulas here. Okay, so this is all good and dandy and everything, but I don't want this in terms of 2 variables. Right now it's in terms of R and H, but I don't want that because I don't know how to differentiate with multiple variables like this. So instead, I want to get it in terms of a single variable. If I look at this triangle right here, I can come up with a relationship that will allow me to solve for R in terms of H. So this triangle here, we have similar triangles. The triangle with the 2 and the 5 are similar to the triangle with R and H, if you think back to your good old geometry days. So I know the proportion of R and H is equal to the proportion of 2 and 5. That is just the law of similar triangles. So if I cross multiply here, I get 5R is equal to 2H. And to solve for R in terms of H, this gives me R is equal to 2/5 H. That allows me to solve for volume in terms of a single variable. So I'm going to replace R in terms of H. So this gives me volume is equal to 1/3 pi. R squared is 2/5 H squared times H. If I square out that term, this gives me 1/3 pi. 2/5 squared is 4/25. H squared times H. And then collecting my constants here, 1/3 times 4/25 gives me 4/75 pi. And then I have H cubed. So this is volume in terms of a single variable. Again, I couldn't have it in terms of two variables because I don't know how to differentiate with multiple variables. Okay, so this is my volume in terms of a single variable. So let's just rewrite it. This is volume. Next, I want to take the derivative of both sides with respect to t. So I have d dt of v is equal to d dt of 4/75 pi h cubed. So over on this right side, I am going to have to use the chain rule. So doing that, I will have that f, the outer function. First of all, I'm just going to focus on the h cubed. I'm going to bring this 4/75 pi out to the front using the constant multiple rule. So let's just focus on that h cubed to find the derivative of that. So my f, my outer function, will be x cubed. My inner function will be h. That makes f prime 3x squared and g prime equal to h prime of t. So then f prime of g times g prime equals 3h of t squared times h prime of t. So plugging this back in, I get dv dt is equal to, I brought my constant up front, 4 pi over 75. And then I have the derivative of 3h of t squared times h prime of t. So just to remind ourselves, I want to know h prime of t, or dh dt. That is what I'm trying to solve for. And I know dv dt, and I know h of t. So plugging in everything I know, well, I know that the volume is changing at a rate of negative 2.25 cubic inches per minute. And then I have 4 pi over 75 times 3. My h, my height, is 3 inches. So I get 3 squared times h prime of t. If I divide both sides now by 4 pi over 75 times 3 squared, 4 pi divided by 75, 3 times 3 squared, I get h prime of t is equal to negative 0.497 inches per minute. Does this make sense? Well, it makes sense that it's negative since my coffee is draining, so the height is decreasing. And the number makes sense given the maximum radius of 2 and maximum height of 5. My units here are inches per minute since I am changing my height, that is inches, and my time is minute. Does that make sense? I know that these examples are pretty long and involved, so I do recommend that if you get stuck, if you're confused as to where I got something, rewind the video and watch this example again. Okay, we have one last example. An observer stands 200 meters from the flat launch site of a hot air balloon. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after the balloon was launched? All right, let's draw a picture. So I have a balloon that is traveling upwards. That's my balloon. Again, I know it's beautiful. And I have an observer who is standing, if this is the launch site, right? Our balloon is traveling vertically upward. My observer, person here, is standing 200 feet away from it. And the observer looks up at the balloon like that. So this is a right angle. And we want to know how fast the angle of the elevation is changing. So my angle of elevation is here. I'm going to call it theta of t. So I'm going to call the distance between the ground and the balloon y of t. Yeah, I'll just leave it at that. All right, so what do I know? Well, I know, we know. Let's see, so the balloon rises at a constant rate of 4 meters per second. So that means that dy dt is equal to 4. I know that the time that I care about is 30 seconds. And what else do I know? Well, it might be helpful to know what the height of the balloon is after 30 seconds. So since it's rising vertically at a constant rate of 4 meters per second, after 30 seconds, our height y of 30 seconds is equal to 120. That is just 30 times 4. So let's draw another picture here. I care at time equals 30, so this will be 200. At time equals 30, this will be 120 feet. This is my angle here. Using the Pythagorean theorem, plugging in 200 and 120 into the Pythagorean theorem gives me this is equal to 233.24. All right, so I'm going to leave this picture alone for just a second. So we know this. What do we want to know? Well, we want to know how fast the angle of elevation of the balloon is increasing. So I want to know d theta over dt, or theta prime of t. That's what I want to know. So how are all of these variables related? How are y and theta related to each other? Well, they are related through our favorite math ever, trigonometry. So I know that how are theta and y related to each other? If I look at this triangle right here, I see that if I take the tangent of theta, I get tangent of theta is equal to opposite over adjacent, which is y of t over 200. And remember, theta here is it is a function, not a variable. So this is how they are related. So the next step is to differentiate both sides. So when I differentiate, I'm going to have to use the chain rule on tangent of theta of t, because I have a function, theta of t, inside another function, tangent. So over here on the left-hand side, I'm going to have to use the chain rule. That makes my outer function tangent of theta, or x if you want, and my inner function theta of t. That makes f prime secant squared of theta and G prime is equal to theta prime of t. So then f prime of g times g prime is equal to secant squared theta of t times theta prime of t. Okay, so plugging this back in, on the left-hand side, my derivative was secant squared theta of t times theta prime of t. The derivative on my right side, since I just have a single function, it's just y prime of t. Okay, well, I want to solve for theta prime. That is what I am after. Let's go ahead and plug in what I know. So I know that y prime is equal to 4. That's dy dt. So that's one thing that I know. What about the angle? Do I know the angle at a certain point? Well, yes, I certainly do. If I use this triangle here, I can solve for the angle when t is 30 seconds. So there are a couple ways I could solve for this angle. I'm going to use cosine. So cosine of theta is equal to adjacent over hypotenuse. So if I take the cosine inverse of 200 over 233.24, in terms of radians, this is 0.86 radians. Okay, that is my angle. So I have, let's see. So this is secant squared of 0.86 times theta prime of t, that's what I'm trying to solve for, is equal to 1 over 200 times y prime of t. That is what I am solving for. Oh, excuse me, that's what I know. Sorry, I know y prime of t. That's equal to 4. Okay. So actually, I'm going to rearrange this so that we don't have to take secant of this, since I solved for this using cosine. So if I were to isolate theta prime, since that's what we're solving for here, I'm going to divide both sides by secant squared of theta. So hold on tight real quick. To get theta prime of t is equal to 4 over 200 is 1 over 50. So I get 1 over 50 over secant squared of theta. So here I have 1 over secant squared, or 1 over 50 over secant squared, which is the same as 1 over 50 times cosine squared of theta. And I know what cosine of theta is. It's this guy. So, yeah, sorry, I think I wrote down the wrong thing here. So that means that cosine of theta is equal to 0.86. So I plug in 0.86 right here for cosine theta. You could have solved for secant theta. It's just nicer to use cosine, I think, for most of us. And that's how it rearranges. So I get theta prime of t is equal to 1 over 50 times cosine theta is 200 over 233.24, which is 0.86 squared. And solving for this gives me theta prime of t is 0.015. What is our units? It's an angle, so it's changing in terms of radians per second. So, does it make sense that our angle is increasing? Well, it does, because as the balloon rises, our angle will increase, so our theta prime should be positive, and it is very slow, since angles do change pretty slowly when we're talking about hot air balloons and stuff like that. So this answer does make sense. So just to clarify, I I wrote down, I think, cosine inverse of 200 over 233.24 was equal to 0.86. That was incorrect. So 200 over 233.24 is 0.86. So that is the cosine of theta, which I plugged in for this guy, since when I divided by secant squared of theta, I got 1 over secant squared, which is the same thing as cosine squared. So that's what I did there. Let me know if you have any questions on this example or any of the other examples in the Zoom session. I would love to see you there. And I think that is it for today. So yeah, I hope to see you at the Zoom session. If not, I will see you on Wednesday. Have a wonderful day.